we're looking at is hypothesis testing. Today, we aren't really doing any hypothesis testing. We're just trying to understand the notation and a couple things that go along with it. So this should be a one-day section, I think. Example, a friend wants to play a simple coin flipping game. If the coin lands heads up, you win. If it lands tails up, your friend wins. So suppose you play 5 times and you get it, and it's tails every time. Is your friend cheating?
Yes.
Yes?
I mean,
There's
probably,
no way. Yeah.
Probably, but mathematically speaking,
Okay,
not.
it could happen, couldn't it?
But
How likely
it's
is
not
it to
likely.
happen?
Not very at all.
So what's the probability of getting a tails the first
It would
time?
just be 0.5 times 0.5 times 0.5.
Yeah.
Or
Well,
5
1/2.
times 0.5.
One. So you'd have to multiply 0.5 5 times, right?
Yeah.
Kind of just write it to the 5th. So if we do that,
1% chance.
Yeah,
okay,
it's
so that's
unusual.
unusual. So either your friend is very lucky,
Tails.
Or it's rigged.
yeah, maybe they have a weighted coin. So either they're very lucky or they're cheating. It could happen. Just knowing the fact that it's only 3% chance, does that mean your friend has to be cheating?
No.
No, because it could happen. It's just not likely. So hypothesis testing, it's not really a guaranteed thing. We're going to decide, do we accept this or not? It's not necessarily a guarantee because we know things can, if it's not impossible, there is a chance that it happens. But we're looking at what's significant enough to make a conclusion. So, in general, a hypothesis is just a statement regarding a characteristic of a population. You've seen that term before in your science classes. It's just a guess about what you think is going to happen. Couple examples, in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So their hypothesis is it's not 62% anymore. Or, according to a study published in March 2006, the mean length of a phone call on a cell phone was 3.25 minutes. A researcher believes the mean has increased since then. So they think now the average is more than 3.25. Okay, so their hypothesis is just their guess about what they think. Now, if you actually had the data from the entire population, there would be no need for inferential statistics for me to make guesses. If I want to figure out how much my statistics students study in a week, okay, do I need to make guesses about it, or could I actually take my entire population of statistics students and get how much they study in a week? Would there be any need for me to make the guesses there? No, because the population is available. So this whole idea of hypothesis testing is really only relevant if you can't get the true information, if we can't look at the entire population.
I don't think you should actually do that because I think you'll be great at this.
I'm going to live in my happy little world and pretend that you do.
Yeah, but how do you really study math? Yeah, but if
I just
already
look at how I work.
Yeah, I just stare at the study guide and hope
Better
it's
option would be to cover up your answer and rework it.
That's a lot of effort.
Just saying. Alright, so in hypothesis testing, that is our procedure based on some kind of evidence that tests a statement about our population. The steps that we are going to go through, really we're not even getting through with all of these steps, but these are kind of the things that are done. You have to make a statement regarding the population. For us, most of the time that statement's already going to be given. Collect the evidence. That's all going to be given to us in the problem. And then analyze the data. That's really the piece that we are going to be working on in this chapter. We're going to be looking at the data and deciding if we believe the statement or not. The big terms that are important for you, so these are the key things. The null hypothesis, that's H sub 0. That is the statement to be tested. The alternative hypothesis is your H sub 1, and that's what we are trying to find evidence to support. The null hypothesis is always assumed to be true unless the evidence indicates otherwise. So the null hypothesis is what we are going to assume to be true, and then we're going to look at the data and see if we can change our mind about that. That is the big thing we are going to be looking at today. In a few minutes, we are going to read a bunch of examples and just list the null hypothesis and the alternative hypothesis. That will be the first step on every problem that we do for the rest of this chapter. It's just reading the problem and picking out which is which. Okay?
They give you the null and you have to find the other.
It'll tell you both of them. You just have to figure out which is which in the problem. In general, as we are going through this chapter, there are going to be 3 different ways that we can set them up. The null hypothesis is always going to be the same. The parameter is equal to some value. The average is 62%, or the mean is 5, or p-hat is 0.4, something. That's the same every time. The difference is the alternative hypothesis. We can either say it's not equal to a value, it's more, or it's less. So if my null hypothesis was that the mean is equal to 5, then the 3 different alternative hypotheses I could make would be the mean is not 5, the mean is greater than 5, or the mean is less than 5. Okay, those are the options that we will look at. These have names given to them. The first one, the not equal, is called a two-tailed test. You know, if you think about what that means, if we're trying to say, okay, I've got some value and I'm trying to show it's not equal to that, it could be bigger or it could be smaller. So it's two tails. You could have answers in either end. A left-tailed test, if I'm trying to prove something is smaller, then I want to prove the real value is to the left. A right-tailed test, you're trying to show that it is bigger than a value, or you're trying to show it's to the right. So those are the different tests. Sometimes we might just hear that term two-tailed or right-tailed or left-tailed. Two-tailed just means it can't be equal, so it's bigger or smaller. Right-tailed is bigger, left-tailed is smaller. Any questions so far? Let's look at an example. For each of these, I want to find the null and alternative hypothesis. And then we'll decide if it's two-tailed, left-tailed, or right-tailed. So, kind of going back to those examples. In 2008, 62% of adult Americans regularly volunteered their time for charity work. A researcher believes that this percentage is different today. You have to use correct labeling. The null is H sub 0, the alternative is H sub 1. So my H sub 0. Yeah, so it's like saying my P, my proportion, is 0.62. Alternative, what does the researcher believe? It's different, so that would be saying it is not 0.62. Is that left, right, or two-tailed?
Two-tailed.
Two-tailed.
So all you have to do is two-tailed, you have to draw a picture.
Okay, take a second and look at B and C. See if you can do those. According to a study published in March 2006, the mean length of a phone call on a cell phone was 3.25 minutes. What is that?
That's what I mean.
Right, so the null hypothesis is the mean, mu, is 3.25.
I think this researcher is wrong. Like, I'm on the phone for a max of 30 seconds.
Yeah, I would say.
Yeah, that was definitely decreased.
The alternative hypothesis, the researcher believes that the mean has increased, so mu greater than 3.25. Okay, so is this left right,
Right.
or to. Greater than means to the right, so this is right tail.
Like the little guy's pointing to which side.
Mm-hmm.
You know,
There you go.
little fella.
Using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. So the null hypothesis would be, standard deviation means sigma is 0.23. With new equipment, the quality control manager believes the standard deviation has increased. So the alternative would be sigma is less than. And that would be left tail. Less than is to the left. Okay. So that's the first thing that you will do on every problem in this chapter. Read it, write down the null and alternative hypothesis. Any questions about those? The next slide. This is important. You need to remember what these mean. So there are two types of error that we encounter, type 1 and type 2 error. Type 1 error is we reject the null hypothesis when it is true. So it would be like me working a problem and saying, okay, I think the alternative hypothesis is correct, I'm rejecting the null, but I'm wrong. The null hypothesis was actually true. Type 2 error, we use alpha for type 1, type 2 is beta, is when we do not reject the null when we should. So if we reject it and we shouldn't have, that's alpha, type 1. If we don't reject it and we should have, that's beta, type 2.
How do you know whether it's wrong?
Well, it would be based, we wouldn't necessarily know just from doing a problem, but it would be like if there were outside influences maybe impacting the numbers that could have skewed the data we had.
So it will kind of give us more background information.
Yeah. Yeah. Alpha is the level of significance. That's the probability of making a type 1 error. As the probability of type 1 goes up, so if we become more likely to reject the null hypothesis, then beta is actually going to go down. They're kind of inverse. So when the probability of one's going up, the other goes down. When the probability of one goes down, the other one goes up. Really what you need to know for now is which is which. So I might give you a scenario and say, okay, give me the examples. What would be a type 1 error? What would be a type 2 error? Or I might say, okay, this happened. Which type of error was it? So you do need to know which is which. So that's what we're going to do now. Take a few examples and we're going to identify the different types of error. So for each of the following claims, explain what it would mean to make a type 1 error and a type 2 error. So back to our example. In 2008, 62% of American adults regularly volunteered their time for charity. Researcher believes the percentage is different today. So type 1 error means we reject the null, but it was true. So it would be like the researcher concluding that the p was not 0.62 when it actually was. So the researcher thinks their null hypothesis is true, but they're wrong. It was really, or they think their alternative hypothesis is true, but it was really the null. Type 2 error is when we don't reject it, so we believe the null, but really the alternative hypothesis is true. So that would be the researcher concluding that p is 0.62 when actually it is not. Why don't you guys do the second example? Find the phone call. So type 1 says you reject the null when it's true. If we think back, we did in the example 2, we did the null. So type 1 would be when I reject this. So I'm saying the alternative is true. The mean is bigger than that. When in fact the mean is actually still equal to the 3.25. Type 2 is when you don't reject it, but the alternative is true. So type 2 would be when the researcher says, okay, this was right, the mean is 3.25, but in reality the researcher is wrong, and it is bigger. Questions there? Alright, so basically type 1 error is when you assume the alternative is true. Type 2 error is when you conclude that the null was true, but you are wrong in both cases. That's why it's error. As we move forward, we're going to be testing hypothesis. We will never just accept a null hypothesis. The terminology we will use is either we reject it or we fail to reject it. Because we don't have all the information in the population. We can't, with 100% certainty, say this is not true. We are just going to say, this is not true, or I can't prove it's true, but I can't prove that it's not true. So we'll either reject or fail to reject, and we'll look at that more in the future sections. So last example, according to a study, so this is back to our phone call. Part A, suppose the sample evidence indicates the null hypothesis should be rejected. So we did this testing. Our evidence says the null hypothesis is probably not right. We need to reject that. So our conclusion, we would say there is sufficient evidence we have enough proof to conclude. Remember on this one we said the null hypothesis was that the phone call, the mean length was 3.25, and the alternative was the mean is greater than 3.25. So if we are rejecting it, that means we believe the other one. So there's sufficient evidence to conclude the mean phone call length. We did it in example 2. We stated the null one. Is greater than 3.25 minutes. We didn't say with 100% certainty, I know the average phone call length is more than that. We just said there is enough evidence for me to conclude that this is probably true. Part B, suppose the sample evidence indicates that the null should not be rejected. So that doesn't mean I say the mean phone call length is 3.25. I'm just saying there's not enough evidence for me to believe otherwise. There's insufficient evidence. To reject the null hypothesis. So we conclude the null is true. Or we fail to reject it at least. We can't say that it is most definitely true, but we can't prove otherwise.
So I could have put like, instead of like the fail to reject, I could have put like there's not enough evidence to conclude that the mutual is true.
Exactly. We don't have enough evidence to prove otherwise. That doesn't mean that this is true, it just means I can't prove that it's not. Okay. Is that alright? Not a lot of math in this one, really just interpreting things.
Not okay?
That's okay? Alright, so we've got some time now. And here is the assignment.